Hello and welcome. In this tutorial, we will demonstrate the new concept of virtual signals introduced with the 2022.4 software version of Typhoon HIL Control Center. Virtual signals are a special type of signals that can be defined in the capture mode of the capture scope widget. Those signals are generated through user-specified functions and are intended to be used for offline analysis. The main motivation for this feature is to create high-resolution signals without an additional burden on HIL device. It also provides wider flexibility for utilizing specialized Python analytical modules such as NumPy, SciPy, pandas, and math. To see how this new software feature actually works, we will use a simple electric drive model. Let's compile the model and load it to HIL SCADA. For the demonstration, it will be enough to insert a capture scope widget. Let's open it and switch to the capture mode. When we click on signals, we can see that the capture signal properties has an additional button, virtual signals. Let's click on it. In this dialog, we can create a new virtual signal or edit or delete an existing one. Let's create our first virtual signal by pressing the plus button. The virtual signal settings dialog consists of 4 pods. In the first text box, we can specify the virtual signal's unique name. Since this model only has phase to neutral voltage measurements, let's create a phase-to-phase measurement VAB. Below it, we have a combo box for specifying whether we want to plot a signal as analog or digital. We will keep it as an analog signal. After that, we need to add input signals that will be used for calculating the virtual signal. Let's add the VA and VB signals. If we want, we can rename argument names to more descriptive names. For example, let's name the first signal as VA measured. We can see that the dialog automatically renames argument names according to snake case variables start with the lowercase, and an underscore is added between words. We will rename the second argument accordingly. The most important step is the definition of the transform function. Here it is important to remember that the return statement is expecting a Python collection of numerical values in the form of a list or an NumPy ND array. In this case, we will return a simple statement that subtracts voltage VB from VA. At the end, we can press the validate code button, which will evaluate the transform function. If it validates successfully, we can click on the save button. Now that the signal is successfully created, we can close the virtual signals dialog and add it to the list of capture signals. It is important to notice that the number of virtual signals that can be captured is not limited. This can be a useful trick if you want to spare some capturing resources in your HIL device. Now, let's click the force trigger button. As we can see, the virtual signal is not captured, and in the message log, we can observe the warning that input signals VA and VB are missing. It is important to remember that all the input signals must be captured in order to plot the virtual signal. Let's add them and the capture signals again. Now that all the input signals are captured as well, the VAB signal is successfully plotted. Note that we can use the same strategy to generate a neutral current measurement from phase current measurements. In the rest of the tutorial, we will demonstrate some other use cases of virtual signals. Here we can see the creation of a simple threshold signal that has a constant value of 3. It can be useful in case we want to track the reaction time of some protection algorithm. Another virtual signal use case is the scaling of different signals or creating ad hoc signals without spending real-time resources or the need to recompile the model. As an example, here we are scaling the machine mechanical speed from radians per second to RPMs. Apart from generating new signals and scaling existing ones, the virtual signal frame can also be used for better visual representation of signals. For example, in this model, The three-phase inverter is controlled by an external controller. If we want to display digital signals corresponding to PWM signals, we may want to create aliases for those signals. It can be really useful to offset those digital signals, so we can observe all of them in a single viewport. Let's demonstrate this functionality. Virtual signals can also be used for dead time visualization. This can be done by comparing the PWMs controlling the upper and lower IGBTs of a single edge. Note that this visualization can be done with the resolution of a single simulation time step. Finally, let's look at how more advanced functions that use Python libraries such as SciPy can be used for generating digital signals. Here we filter the PWM signal coming to the digital input of the HIL device. In this way, we can estimate the dilating signal of the controller, which can be of huge help during the development process. In a similar way, more advanced analysis such as THD and other harmonic analyses can be done. Let us know in the comments what would like to see more from virtual signals. Thank you for watching.